Okay, I think I'm recording. Okay, yes. Lights. Okay, what do you need to know? Okay, so like all the while I've been saying, like it's a very big topic. Okay, it's a topic where some students will usually traditionally will struggle with. Okay, that's why from the start I tell you all need to come, be close and all these and make sure you understand. But I think along the way sometimes some of you miss lessons here and there. So that gap will have cause some like the gaps in the understanding. So light, three main areas: reflection, refraction, and and lenses. Okay, so key things to know for reflection. First thing is, how do you see things? Basically, luminous object will emit its own light. Non-luminous, you need to see from a reflection light, so it just bounces off. Okay, then we represent light with straight lines and arrows. So I think I did mention also in class today, okay, where we draw light, always straight line with arrows. Okay. Then so we move on to the laws of reflection. Okay, or before that, just some information about light. Okay, key thing is you are expected to know that light travel at a speed of 3 × 10⁸ meters per second in vacuum. Okay, so this is something that during exam, okay, we can get you to do assuming that you know this value. Okay, because a lot of other values like g equals to 10, the kind of things we always give, but then somehow speed of light is something that I expected to know. Okay, maybe I show you all the syllabus document. Okay, why speed of light? So yeah, so because in the following chapter on electromagnetic spectrum, okay, on chapter 14, we're expected to be able to state the electromagnetic waves. They all travel at the same speed and state the magnitude of this speed, which is the 3 × 10⁸ meters per second. Okay, so you're expected to know this. Okay, we will come to this chapter again, but the 3 × 10⁸ is like, yeah, you're expected to know. Okay, so laws of reflection. First law, not so important in the sense that we don't really discuss it as much. It's mainly a second law, which is pretty straightforward. Angle of incidence equals to angle of reflection. Key thing to take note when you measure the angles, you always measure from the normal. And what's the normal? The normal is this imaginary line, okay, that's perpendicular of the point of incidence. Okay, so wherever you're reflecting off, it could be a curved surface, it could be a straight surface, it will be perpendicular to that surface. Okay, so then angle of incidence, angle of reflection, just measure from that. Okay, so sometimes the trick is they will like to give you at the other side. Then you have to go and like calculate, make sure that it's 90 minus that, whatever not. Yeah. Okay. So the examples I think are key. So because the reflection quite straightforward. Okay. So types of reflection, you have your regular reflection and your diffuse reflection. Basically the smooth and the rough surface. When we talk about smooth and rough, we are looking at these surfaces at a microscopic level. Okay, so like for example, you touch your table very smooth. It doesn't mean that it's a smooth surface. Okay, so it's actually microscopically considered rough. That's why you cannot see a perfect reflection of your table. Okay, so at any surface you can see the very nice reflection. Okay, we can call that a smooth surface. Okay, then you need to know the 5 characteristics, okay, of a plane mirror image. Okay, so plane mirror, okay, refers to a flat mirror. Okay, so you need to know the image. Okay, what is the characteristics? Okay, there's 5. Okay, when we are discussing about lenses, we always look at 3 things only. Okay, we look at whether for lenses, we jump a little bit to lenses. So far, we have discussed about characteristics of images in the lenses. We talk about whether it's real or virtual. We talk about whether it's upright or inverted. We talk about the size. Is it same size, magnified, or diminished? For plane mirror image, there's 2 other properties that is being discussed. One is that it is laterally inverted, meaning left become right, right become left. Another one is that distance from the mirror, okay, the distance of the image from the mirror is equals to the distance of the object from the mirror. Okay, sound a bit long, don't know what I'm talking about. Basically, is just say that image distance equals to object distance. Okay, every time we say about image distance or object distance, you refer to the distance between the object and the lens, or the object and the mirror, or the image and the mirror, image and the lens. Okay, so that's what I call object distance or image distance. Okay, so basically in this case, so yeah, take note. So I repeat again, you need to know all these 5 you are expected to know. Virtual, okay, it's not real, okay, it cannot be captured on the screen, you know, you can see it is, but technically there's nothing behind it. Okay, it is upright, okay, you don't become upside down, it's same size. Okay, so these 3, once you know, then the last 2 is just laterally inverted. Image distance equals to object distance. Okay, now that we have done your lenses, I think this will make a little bit more sense. Construction of ray diagram. Okay, this one you can go and watch the video, but just a quick recap. Okay, step 1, locate your image, making use of the property that object distance equals to image distance. Okay, so your object, you can measure what is this distance, your image you measure the same distance. Take note, it's a perpendicular distance. Okay, so you don't when the, for example, in this question, okay, the image is C, not B. Okay, so some people think that, oh, it must be directly opposite, so my image should be B. Okay, no, your mirror is not a bit slanted, so you'll be like that away from the mirror, so you'll be equidistant away from the mirror this way. Okay. So once you located the image, next thing is where you are looking at the image. Okay, your eye will assume that, you know, the light is coming from there. Okay, so you will just draw a straight line over. Key thing, okay, every time I said before, virtual is always dotted. Okay, it's not real. Okay, if it's a real light ray, then you use solid line with arrows. Okay, anything behind the mirror is dotted. Okay, because it's virtual, there's nothing behind the mirror. Okay, then the last part is just to join the object over to here. Okay, I just realized Xavier joined the here, but the combined science haven't learned light yet, right?
Sure. They haven't learned.
Yeah. Okay, never mind. You just listen if you want to listen. Okay, anyway, so yeah, so ray diagram. Okay, some applications for mirror. These are some of the applications. Okay, so for example, if you are in those vision testing room, okay, like I said, the chart can be placed behind you, but when you look at the image of the chart through the mirror, okay, you'll be much further away. Like in this case, even though the room maybe is only a 3.5 meters room, but I can make you look at something as if it is 6.5 meters away, okay, in a very small room. Okay, so this is the one of the applications. Here I point out this morning, specific application you all need to know is optical fiber, okay, fiber optics, but all these are just general one, you don't need to must know, but the fiber optic one, okay, is a must know, okay, because here they got specifically mentioned that, you know, you are supposed to be able to state the advantages of the use of optical fibers. Okay, so this one is they got say one, so you must know. Okay, so yeah, basically you can see what are some of the things you need to know. Reflection, you need to know reflection, what is normal, what is angle of incidence, what is angle of reflection. Okay, you need to know the angle of incidence is equal to the angle of reflection. Okay, use this in your constructions, your ray diagram and all these, do calculations and whatnot. Okay, so yeah. Then yeah, this one, there's another example, okay, how your voltmeter, ammeter can use of a piece of mirror to help you, you know, prevent parallax error, okay? So if your eye is not directly perpendicular to this needle, you'll be able to see this reflection over here, okay? Because there's a piece of mirror underneath, directly underneath the scale. You can see this image, you can see a reflection, means your eye is not perpendicular. If it's perpendicular, the object itself should block the image, so you cannot see the reflection. Okay, so next year when you do electricity experiment, we'll read, make sure you don't see the reflection. Okay. Then periscope, I think some since what primary school got talk about this lah, you can use a periscope. Okay, as in use mirror to make periscope. Okay, if not, that is all about reflection. So far, any questions?
No.
Okay.
Mr. Wong,
Yes.
to explain the characteristics, right? There's one point which is laterally inverted. Must
Yes,
we write
laterally
the word
inverted.
lateral? Must we write the word laterally, or can just put inverted? Can you?
There's a difference between laterally inverted and inverted. Inverted means upside down. Laterally inverted means left become right, right become left. So it's different. You need to write the word laterally.
Okay, thank you.
Okay, good. Yeah, okay, got this kind of questions very good. This one will really try to understand. If not, you're not sure, then I also don't know what you're not sure of, right? Because yeah, like if Joshua never highlight this, I wouldn't know that, oh, he might be thinking of whether can just write inverted. Okay, so yeah. Okay, now we move on to refraction. Okay, so I did discuss refraction this morning when I recap again. Okay, so basically, why does refraction occur? Okay, because light travels at different speed. Okay, in different mediums. Okay, so when they travel across different mediums, this speed changes, and this change in speed causes the light ray to bend. Okay, but this bending, okay, what is the effect on terms of how we observe things? Is that because when we look at things, our eyes automatically assume that light travel in a straight line. Okay, so because of the way our eyes perceive things, okay, our eyes will auto extrapolate itself and think that, oh, this is how it's going to look like. Okay, we'll produce its own image. Okay, so because of that, when we look at things, it will appear a bit distorted. Okay, so okay, yeah, okay, basically, yeah, never mind. So refraction, okay, light travel always fastest in a vacuum, okay, and then it slows down in any optically denser medium. Okay, so this morning I also said make sure you use the word optically, don't just use denser. Okay, but of course when we discuss in class, okay, we'll just use dense and less dense and that kind of stuff. Okay, but when you write, make sure you write the word optically denser. Alternative word, if you don't want to use optical density, is refractive index. Okay, optical density, there's no quantitative measurement to it. I cannot say there's an optical density of how many. There's no number to it. But refractive index there is. Okay, so if something is optically denser, you will have a higher refractive index. Okay, we'll come to that again. Okay, sorry. Yes.
I have another question. So like normally if you want to identify whether it's going to a denser or less dense, right? How do, like for example, like normally if you are doing for less dense to denser medium, how the arrow look like?
Okay, I'll come to that. Okay, come. So over here, okay, so same thing. Before I even start to talk about those bending of light, okay, you need to recognize, okay, same thing. Your normal is perpendicular to the surface. Angle of incidence and angle of refraction also measure off the normal. Okay, key thing is when you go through, it must go across to the other side. Cannot. My light ray come from here, then suddenly go here. Cannot. Okay, you will go across to the other side. Okay, so key thing, okay, I think this one we said before a lot of times. If it's traveling from less dense to denser, it always slows down and it bends towards the normal. Okay, slow down will go towards the normal. Okay, doesn't matter which direction you come from. Meaning if you come from top to bottom, okay, once it slows down, you also bend towards normal. Okay, you go from left to right, right to left. As long as it slows down, you go towards your normal. Okay, so like in this case, top to bottom, it goes from less dense to denser. It slows down, it bends towards the normal. Okay, so the direction doesn't really matter. Okay, of course, this weak reflected ray, usually you don't need to draw, but I just need to know that, yeah, just like, sometimes you look through the window, you can see a bit of a reflection because of this weak reflected ray. Okay, so yeah, but most of the light should still pass through. Okay. Okay, so back to the question, okay, on the bending. Okay, before we go to bending, we talk about refractive index. Okay, so just now I say optical density, okay, the version of it that is quantitative, that you can say that there's a number to it, okay, is we call the refractive index represented by a symbol of n. Okay, basically it's defined, okay, as the ratio of the speed of light in vacuum to the speed of light in medium. By now you realize that this formula is not as common as n equals to sine I over sine R. Okay, because a lot of times when we do angles calculations, we talk about sine over sine R, that to the extent that people will start to think that, oh, sine I over sine R is just my definition of N, refractive index. Actually, no. Okay, refractive index is defined, okay, as the ratio of the speed of light in vacuum, okay, to the speed of light in the medium. So in this case, I do not need to give you C. Okay, we know that C is 3 times 10 to the power 8 meters per second. Okay, then with that, okay, you can just go and do your calculation. Okay, I don't need to give you YC. Okay, so example question. I think this one, nothing much. I'll just start and get answer right. Oh, okay, quite easy. Okay, I shall skip. Okay, later I go to maybe those more exam style of question. Okay, then we look at it together. Okay, so now, okay, the more common formula, okay, N is C over V, okay, is also equals to sine I over sine R, okay, where I is the angle of incidence in vacuum, R is the angle of refraction in the medium. Okay, so you always, when it goes from vacuum to medium, it bends towards the normal, so you'll be from a larger angle become a smaller angle. Okay, so yeah, and then when you always take something bigger divide by something smaller, N will always be larger than 1 lah. Okay, so yeah, but then if let's say you are traveling from denser to less dense, okay, when you are traveling from optically denser medium to optically less dense medium, you speed up, and when you speed up, you move away from the normal. So you move away from the normal, now angle of refraction is bigger. Okay, so now we will flip around the equation. Okay, you're traveling from denser to less dense. Okay, we will use sine R over sine I. Okay, in your textbook, you realize that if you read your textbook again, they will not mention anything of this. Okay, in the textbook, they just say what principle of reversibility or whatever, not like that, but basically it's just this lah. Okay, I already have a formula for you. Okay, I hope that it is clearer. Okay. So put side by side to compare. Okay, this slide was is not from them. It is I own self create one. Okay, so anyway, let's say we are traveling from vacuum into a medium. Okay, you use N equals to sine I over sine R. If you're traveling from a medium into a vacuum, is N equals to sine R over sine I. And you'll notice that the angle on top will always be the larger angle. Is always the angle in the vacuum. Okay, the angle below will always be the smaller angle, and it will always be the angle in the medium. Okay, so yeah, I hope this is clear. Yeah, okay. You are not expected to memorize any refractive indices. Okay, yeah, during the question they will just give you accordingly. Okay, but at secondary school we can treat that, you know, speed of light in air is the same as speed of light in vacuum. Okay, so they are the same thing. Okay, about the same. Okay, if you enter an object, okay, a medium, okay, with an angle of incidence is 0, you will not, the light will not change direction. Okay, it will just go through straight. Okay, so if it's other ways of describing this, okay, sometimes you go and see 10-year series or what, they can say that, oh, the light is entering the medium perpendicularly, or they can say that the light is entering normally. Okay, even they call it normally. Okay, it's spelled normally like how your normally is being spelled, but that normally refers to it goes along the normal. Okay, it's called normally. Okay, so yeah, so if something enters normally, it means that the angle of incidence is 0. Okay, because we measure our angle from the normal. Okay, it goes along the normal, then 0 lah. Okay. Am I too fast? I think she will okay, right? This one is more like a recap. Okay, so basically, calculation wise, so for example, in this example, okay, ask you to data refractive index is 1.3. Ask to complete ray diagram. Okay, so angle of incidence here is 60. Okay, not 30. Okay, take note. Always measure from the normal. Okay, so it's 60. You just do your substitution. Angle of incidence is 60. N is 1.3. Then you find R. Key thing to take note over here is to do the sine inverse. What do I mean? Okay, for those people who haven't done a single question for this, okay, what I mean by I need to do a sine inverse is this. Okay, so your sine R is equals to sine 60 over 1.3. Okay, then how you do the sine inverse? R is equals to sine inverse sine 60 over 1.3. Okay, then you will get this. Okay, so sometimes people will forget to do a sine inverse. They sine 60 over 1.3, key get, then that's the answer. They forgot to do the sine inverse. Okay, so that's the key thing to take note. Okay, then it's 41.8, so it bends towards the normal. Okay, like we have discussed. Okay, after that is just example okay, of using n equals to sine over sine r. Okay, like I said, later we go to a full question where you see how all these can be combined together to be tested on you. Okay. Okay. Then after that I have examples of it exiting. So if it's exiting, I use sine r over sine I. Okay. So now over here you can see it's traveling from glass to air, denser to less dense. Okay, so now it will speed up, it bends away from the normal. You can see that it goes away. Okay, so some of you are asking questions on, when, let's say the question asks about drawing this kind of thing. Okay, how accurate do you need to be? If the question asks you to draw to scale, then you make sure you draw to scale, use your protractor and all this. Right, the question never asks you to draw to scale. Okay, they just ask you to just complete. You just do a sketch. Then in that case, you don't need to make sure that follows a certain angle, but we need to see concepts such as bending away or bending towards. So if traveling from denser to less dense is bend away, make sure in your sketch we can see that it's really bending away. Okay. So yeah. So this one is just an example. We'll sub in lah. Okay, where yeah, sub in get answer. That's all. So yeah, in summary, this. Okay, so it's traveling from less dense to denser. Okay, bends towards the normal. Denser to less dense, bend away from the normal. Okay. So that is about refraction. Okay, about bending less dense to denser, denser to less dense. Okay, so less dense to denser, not much issue lah. Okay, maybe I just do a quick sketch. Okay, less dense to denser, you will bend towards the normal. Okay, so even if I increase my angle of incidence, I increase this one will still bend towards the normal. Okay, I can increase even more. I have no issue, you'll still bend towards the normal. Okay, but the issue comes, okay, for the bending away one. Okay, what do I mean? If I bend away, now it's denser to less dense, I bend away. Like come here, I bend away. I increase my angle of incidence, it bends away some more. You realize that before I even hit angle of incidence 90, my angle of refraction will already hit 90. Correct? So I can increase until a certain angle. I cannot increase anymore because beyond this angle, I cannot bend away already. It's already bent away to the max already. Okay, so this green color one, we call this the critical angle. Okay, critical angle, okay, like what Zheng was discussing with me this morning, okay, is defined as the angle of incidence in the denser medium such that the angle of refraction in the less dense medium is 90. Okay, if you fully understood, then this definition, technically you don't even need to memorize, it just makes sense to you. Okay, I repeat again. Critical angle is the angle of incidence in the denser medium such that the angle of refraction in the less dense medium is 90 degrees. Make sense? Okay. So in that case, this means that when we are exiting, okay, when we go from less dense to denser, nothing much to discuss. I just always bends towards. But when it's traveling from denser to less dense, now we have different scenarios. 3 possible scenarios. 1, the angle of incidence is smaller than the critical angle. It will exit and bend away from the normal. 2, my angle of incidence happen to be the same as the critical angle, it will go along this surface. 3, my angle of incidence is larger than the critical angle. Okay, so it now becomes larger than the critical angle. Then it cannot bend away. What will happen if you cannot bend away? You will undergo total internal reflection. And total internal reflection obeys the law of reflection where I equals to R. So it follows is now a reflection really. Okay, so 3 scenarios are, okay, so come back to here. Okay, this is the textbook we are explaining. Okay, so go straight out. Okay, so when you're traveling from denser to less dense, it bends away. Okay, so when you further increase this angle of incidence, okay, you realize that there will be a particular angle in which the refracted ray is 90. Okay. So I think Michael is coming in.
Mr. Wong.
Okay, no, disappeared. Okay, yes, Joshua.
Can you wait to the diagram? I want to take a picture.
Yo, my this one
Ayo.
Okay. My this one I anyhow draw one. You take picture of this
Yeah, can.
You draw your own one okay. My I anyhow sketch one. Okay.
Okay.
So then so when the angle of incidence become greater than a critical angle, then you undergo total internal reflection. Okay, so just last week, okay, I was having consultation with Sec 4. We also discussing about light. Okay, there's another way to view this concept of a critical angle. Okay, it's like you want to exit from the denser to the less dense medium. You can imagine a critical angle as some kind of height limit. Okay, people taller than the height cannot get out. They will be rejected and they'll come back. People shorter than it can go up. So you can imagine that if your angle of incidence is smaller than the critical angle, you are smaller than height limit, okay, you can go up. Okay, if you are exactly at the height limit, okay, then you go along here. Then if you are greater than it, then you cannot reflected. Okay, so how do we find out what is this so-called height limit? What is this critical angle? What is this special angle? Okay, there's a formula to it. Okay, here. So critical angle is the angle of incidence in the denser medium, such that angle of refraction in the less dense medium is 90. So we are traveling from denser to less dense, it will be n equals to sine R over sine I. So now my I is C, my R is 90. So n equals to sine 90 over sine C. Sine 90, you key the calculator, realize is 1. So n is just equals to 1 over sine C, or you can say that sine C equals to 1 over n. So you can see that the critical angle only depends on one thing, and the one thing it depends on is the refractive index. So for a particular material, let's say glass or let's say water, it has a particular refractive index. So it has its own height limit. Okay, it has its own critical angle. Okay, it's like a property of the object. Okay.
Mr. Wong.
Yes.
Usually, where is the critical angle?
Come in. Where is the critical angle?
Where? Like, is
critical
it
angle
along
is,
the dotted line?
Okay, critical angle is not where, it's just like a height limit. It's just like telling you that, okay, let's say I'm glass. My critical angle is, let's say, I don't know, I just say a random number, let's say it's 40. Okay, meaning any light that is trying to exit glass, if my angle of incidence is smaller than 40, if I'm glass, I'll let you go up.
So the
If
question
your angle of
will
incidence is larger than 40, then as glass, I will not let you go up. I will make you total internal reflect.
Mr. Wong, then the question will usually give you the information to find the critical angle, or they will ask you, or they will just give it to you lah. Is it?
We will look at some examples. Okay. Yeah. Okay. So I discuss a little bit more, then we jump to examples. Okay. So a few things to take note. Okay. So critical angle. So 2 conditions for total internal reflection that you are expected to know. Okay, light must be traveling from optically denser medium to a less dense medium, and the angle of incidence, okay, must be larger than the critical angle. So it must be bigger than height limit. The height limit will kick you back in. Okay, so and this is the definition of critical angle, which we said a lot of times already. Okay, so some advantages of optical fibers over copper wires. I think you all have copied this down in class also. Okay, I think it's in your textbook also. Okay, you know what? So that's more or less for refraction. Okay, we go to examples. Okay, we use past year paper. Okay, for the examples. I don't know whether I got how much time in class to go through past year paper. Okay, I'll start with the 2019 one. So in that case, why not I will use this time, okay, to go through, like, to look at some of the past year paper from the other years. Okay, then we look at the questions for light. Okay, we jump to the light topic. Yes, Joshua, how can I help you?
May I ask a question?
Yes, come.
Like, so critical angle basically defines like the maximum the angle can go to.
You can say that is the maximum angle in which the light can still exit.
So
Once your angle of incidence becomes bigger than this maximum, then you'll do total internal reflection. If you are smaller than that, it will still let you go through.
So critical angle is just like basically like refracted angle.
Refracted angle. No, it's just like a guide law. It's like for that particular property, for that particular material, if my critical angle is, let's say, 50, okay, that means that any light that when I'm trying to exit from that material, if it's more than 50, then angle is just more than 50, which is the critical angle, then I cannot go out. Total internal reflection will occur.
Any greater always undergoes total internal refraction, right?
Is it just me or everyone else will hear Joshua a bit choppy?
I think it's everyone.
Everyone
And cut off a bit.
Yeah, Joshua, when you're talking, you cut off a bit, so I couldn't really hear very well.
My internet connection is a bit unstable.
Okay, never mind. Okay, if got anything else, later we discuss. Okay. Hey, last year, how come they like never really test light? I scroll
Question
until the.
B6.
Sorry.
Question B6.
Oh, B6. Okay, I passed by already. B6. Oh. Hey, B6 is moment.
Wait, which paper is this?
This is the 2021.
Oh, I was looking at 2020. I was looking at 2019.
Oh, there, got. Okay, it's on the either or question. So some example, let's see. Oh, this one, first one is reflection ray diagram, correct? They say that there's a meter rule, plane mirror, distance between meter rule and mirror is 40 cm. He peeped through here, draw light rays to show how much of the meter rule can be seen by the boy using the mirror. Okay. So in this case, one way you can do this is that step one, this is the object. They ask you to see what? They want you to see the mirror. They want you to see the meter rule. So my object is the meter rule. Okay, so I'm just going to sketch. So equidistance, you measure, make sure it's the same distance away. You draw an image. Okay, so this is the meter rule image. Okay, my meter rule image. Okay, step two, you join the eye to whatever you can see. So in this case, the mirror, the edge of the mirror is the max you can see. So using here, you draw a straight line out here, then a straight line out here. Okay, this is the max you can see, but of course, okay, because I should not just draw straight line. I should be straight line dotted. Because behind the mirror is virtual. Straight line dotted. This one is going towards the eye somehow, correct? Okay. Then where does how to finish this? Okay, so this one, the exact point across will be this side. So actually, what I'm looking at is this point, the light comes over here, rebound, go into the eye. But then when I see, I'm looking at the image. You understand? So same thing over here, this one, opposite here. So this one is a slightly more advanced ray diagram, okay? Not so straightforward as what we...
Wait, so I don't understand the part where you like suddenly from the end come to like the mirror. Like the latest one you just drew.
the last one, right? Okay,
Yeah.
so I take it as the same position as here. Okay, I'm just sketching, but actually it should be the same thing because when you are looking at the image here, basically what is happening is you are seeing the reflection of the object. So if you are seeing at this point, I'll go to the exact same point across. So the light actually comes from here, bounce off. But because our eyes see things as if light travel in a straight line, so when we look through, we see it here. Our own light will go and create, our own eyes will create this virtual ray to assume that, oh, what we are seeing is here. Okay, but in exact what is actually happening is the light comes from here, bounce off the mirror, go into your eye. Then after you do this, so this whole thing must be drawn to scale. Make sure everything is correct. Then I think you can measure the how long. Did you say how much or did you just show how much? No need to really, okay, this is not exactly like, yeah, so then you just make sure you draw this can already. Okay?
Can kind of understand.
Yeah.
Richard, what if you missed out the latest step you drew? Will you get 2 marks?
If miss out the what?
The latest step.
The last step, this one?
Yes.
Hello, then 2 marks. So I would guess 1 mark is for coming out with the image, 1 mark for joining here, maybe the last mark is this. That's what I would guess.
It's 40 cm, right? From the mirror to the virtual image.
Yeah, so here it should be 40 cm also.
Okay,
okay, but of course, this one is just, they say that it's 40 in actual, of course, when you put your ruler down, this is not 40 but you just make sure that if let's say from here to here on your ruler, you measure, let's say it's 6 cm, then here you draw 6 cm, no? Or you measure here is, let's say, 2.5 cm, then here you measure 2.5 cm. Okay?
Understand. Thank you.
Okay, so we come to example question. Okay, they tell that the refractive index is 1.5. The light ray travels at an angle of 70. Okay, so this one, no trick, the angle of incidence is really 70. Okay, then it hits here. Okay, so then they ask you to find what is x. Okay, so this one you make use of your, it's traveling from less dense to denser. So sine I over sine R. Okay, so this one will be n equals to sine I over sine R. So n is 1.5, I is 70, sine R. Okay, so you get an sorry, sine x. Okay, my R happens to be x. So you go and do this yourself. I'm just going to show you the working. Okay, sine 70 over 1.5. Okay, I ask you to find the critical angle of the glass. So I say critical angle is a property of the glass. So in this case, the critical angle, I just use sine C equals to 1 over n, where n is 1.5. So C is equals to sine inverse 1 over 1.5. So you will come up with a critical angle. Okay, key thing to take note for pure physics, all your answer blanks are no units. So you need to go and own self write your units. If you never write units, you'll lose mark here, lose mark there, lose mark everywhere. Okay, so make sure you have your units. So critical angle will be angle, so it will be in degrees. Okay, so then they tell that the refracted ray is incident at point N. Okay, so they tell that, oh, it hits here like that. So they ask you to find what is this angle of incidence here. Okay, so if you know whatever this is, you can see that here actually forms a right angle triangle, okay, because this is a rectangle. So this normal will be perpendicular to this normal, correct? Okay, so then they'll form like a right angle triangle. So this means that x plus y is 90 degrees, okay, because in a right angle triangle, here a right angle, so the other two must be 90. So to find y is just 90 minus x. Okay, so you here to find y, you take 90 minus your x value here. Then they ask you to draw the path taken by the ray of light at point N, explain your answer. So this is where now they have calculated everything. You are ready. Okay, this light is traveling from denser to less dense. We said 3 things can happen. if my y is smaller than the critical angle, it's going to exit, it will travel faster, it will bend away from the normal. Okay, so if it's smaller than critical angle, it will bend away from the normal. Okay, if it is y happens to be the same as the critical angle, then you will travel along here. If y is greater than the critical angle, means total internal reflection, then you will draw like that, where this must be same as y. Are we clear? So these are the three possible scenarios. So which this question is very good. They break it down for you step by step. You have your critical angle, okay, you have your angle of incidence. Okay, so you can just compare. If this y is larger than this, then you tell me that, oh, total internal reflection occurred. Or they say, oh no, they say draw, so you just go there and draw. Okay, you draw, see which one is it. Okay, then you draw, okay, then you explain. So if it's greater, then you say that, oh, because total internal reflection, okay, has occurred. Okay, because the angle of incidence is greater than the critical angle.
So,
Yes.
to determine the part 3(1), right? The angle of incidence y is it just like the 180 minus the
Correct.
x?
Yeah,
Or
it's just geometry. This is a triangle, so 180 minus 90 minus x is y.
Is there another method to do it, or is it the only way?
You want other method. This is 90 minus x. This is 90.
Alternate angle.
So yeah, it's just the other way around.
Alright.
Yeah.
Thank you so
There's not much methods to this. Okay, it's quite a straightforward calculation. Okay.
So,
Yes, Joshua.
for the question, for the calculating of the, like, you know, the right angle triangle, right? Must you state that this right angle, that's why it's 90?
Oh, this one is math, so we are not good. This, sorry. This one is physics, this one is not math, so I'm not going to be very particular to say you must write down, angle sum of triangle 180. No. Okay, physics, we are now marking for your physics concepts, we are not asking for your maths concept. Okay, so we'll just treat it as you know that how to find this. Okay, but I am not going to mark that, oh, you must write the reasoning. If not, I penalize you for presentation. No, don't have. Okay, because this is a physics paper.
Mr. Wong, but I also
Yes.
have another question. Could you go
yes.
back to the ray diagram?
Sorry?
Could you go back to the ray diagram?
Okay, but before that, okay, just a quick one. So here they got say draw. So draw the path taken. So this is where actually you don't know what is the exact meaning. Even if you're going to exit, you can't tell, like, you don't know what is my angle unless you can calculate, because they ask you to draw. You need not be to scale, but like I said, the key thing is you need to show that, let's say if it's bending away, you must really, the light must be bending away. Okay, you don't your light draw like that, then you say, oh, it's bending away. Okay, you must show that it is bending away. Okay, so you must draw it such that you can exaggerate a bit, but make sure that it's bending away. Okay, mine not straight line. Make sure you use a ruler pencil to draw. Okay, make sure it's straight line. Okay, or it is total internal reflection, then you make sure that it is total internal reflection. Okay, so all this is the part about the drawing where, you know, they never give you the exact one. Okay, yeah, Joshua, this one, ray diagram.
So I don't really understand why you draw the arrow from the 0 and the 100.
Why the last one, right? Which is what
Yeah,
Daming asks now. Okay, so this one you can get it right. The image of the ruler. This one, the maximum you can see from the corner, I think you can get it right.
Yes, I think yes.
So it's just the last one. So this one, I repeat again. So when your eye is looking at the image here, actually what is happening? The light from this point actually comes from here, it rebounds back, it reflects back. So you make your eye look as if that is looking at here, but actually it's just a reflection of the object. So I will draw this such that this must be exactly same position as this. So it comes from there. Okay. So same thing for the below also.
So what does the dotted line symbolizes?
The what?
The dotted line. What is the
dotted means
purpose of-
virtual. It's not real. It's behind the mirror. In real life, there's nothing behind the mirror.
So the truth is the object, the image bounce to the thing, and then you reflect mirror, then mirror reflect to eyes.
Yes, correct.
So image to object to mirror to eyes. Can you see that?
Image to object to mirror to eyes. No, it's just object to mirror to eyes. But then your
But
eye
you
will
realize
do
because you always think that you're looking straight in one direction, right?
correct. Okay, so you're
So
looking at the image.
So Dr. Then is trying to symbolize that it is a straight line.
Hmm.
Okay, thank you.
Okay, so I think for 2021 last year only got that one question. Maybe I also just quickly we touch on the MCQ question, whatever examples there are. Okay, it seems like last year they were test on lens. Okay, because it's not every year that we can finish teaching light. Okay, so some years are a bit more rush, then they don't have enough time to teach finish, then they will just stop wherever they are. Okay, so okay, let's see how it's here. Okay, question 28. Okay, so over here you have a mirror tilted at 25 degrees, okay, to a bench. Okay, so a ray of light, horizontal, okay, comes here. Okay, they ask you what is the angle of reflection. Okay, so if this is 25, they say that this ray of light is horizontal, okay, is parallel to the bench. Okay, so alternate angles, this must be 25 degrees. What is the angle of reflection? You need to understand that my normal is here. So my angle of incidence is actually 65 degrees. So of course, my angle of reflection will also be 65 degrees. Okay. Then a girl stands at a distance 2 meters in front of a mirror. So this kind of question come out, you're not very sure. Then you draw lah, okay? So you have a girl here. You have a mirror here. They say that this is 2 meters. Okay, the mirror is shifted 1.2 meters towards the girl. Okay, so now the mirror is now here. This is 1.2. This is 0.8. Okay, how much has the image shifted? Okay, so initially my image, this one look like the workbook question, right? Okay, initially my image is here. Because I stand 2 meters away, so my image is 2 meters away. Now, my image is, since this is 0.8 away only, my image will also be such that this is 0.8. Make sense? It will be somewhere here. Okay. So how much did the image shifted? Okay. So the image will have shifted. So here got about 0.4. Here got about 2. So my answer is 2.4. Okay. So the image from here is shifted. Now it becomes here. Okay, which is 0.8 meters away from this. So here is 0.4 and here is 2, so 2.4. Last question, trick question, and it's not so easy. They combine a few calculations. Trick question because instead of giving you angles measuring from normal, they give you the other way around. So actually this is 40. This is 27. Okay, you can see it's traveling from plastic to air, denser to less dense, it bends away. Okay, so denser to less dense, n equals to sine r over sine I. Okay, so this will be equals to sine r is 40 over sine I, which is 27. They ask you, okay, oh, this one very nice. They give you speed of light in air is this. What is the speed of light in the plastic? Okay, so I also know that for this one, the formula is n equals to c over v. So this means that c over v is equals to this. Because it's the same refractive index, right? Okay, so if the same refractive index means I can do my substitution. C is 3 times 10 to the power 8, yeah, over V equals to sine 40 over sine 27. And just find V. Okay, so this one combines two formula, this one and this one. Okay, and they still add in a trick of whether you know 40 or 27. So there's a lot of pitfalls. Any point you fall, then this whole question will go. Okay, shall we go through also the 2020, the light question? Okay, so just we go through the light questions lah. So of course I don't think in class I might have time to go through. Okay, so we just at least go through some so that, yeah. Okay, all the diagrams are gone. Is there any diagram for this? No, I cannot see a diagram. Yeah, how? Okay, you can see this, you do this as the patient have his eyes tested. Okay, this is the person. Okay, 3 meters away from the mirror. This is the chart. How far away from the patient is the image of the chart? So the chart is 5 meters away from the man, but the image of the chart is actually 8 meters away from the mirror. Okay, so this is 5 plus 3, so this is 8. So this is 8 meters away. They say how far from the patient is the image of the chart. So this is the image. So the distance between here is 11.
Mr. Wong, this concept only applies for mirrors, right?
Yeah.
So if there's a mirror, then usually the image will be virtual and it will be like directly opposite lah. And then the length of, the distance from the chart to the object is the same as the distance from the image to the object.
Object, which object you referring to?
I think I'm saying it wrongly. Sorry, the definition is the image distance to the object is the same as
Object, mirror.
Mirror, sorry, to the mirror is same as the mirror distance to the chart.
Yeah. So basically the object to the mirror, the image to the mirror, they should share the same distance.
It's under reflection, right?
Yeah, correct.
I think I understand better.
Okay. So we jump to the structure. Okay, light usually should be a bit more behind. Okay, during your actual O-level exam, the questions that are arranged by topic. Okay, at least for physics. Is there any light question? Did I miss out again? Oh, since I know light question.
Yeah, I think it's question 8.
Is there section A only, right?
Wait, question 8 of section.
Oh, A.
Yeah.
Scroll too fast, I miss out. Oh, yes. Okay, yeah. So this one don't have, okay, so question 8. Okay, let's take a look together. Okay, so question 8. Okay, figure 8 shows a side view of a water-filled aquarium, PQRS, okay, an electric lamp surrounded by a shield, okay, with a narrow transparent slit is immersed, okay, so then it shines over here. The light ray from the slit shines on the water surface at an angle of 50 degrees as shown. By calculating a critical angle of water, explain why light will be able to emerge from the water surface. Okay, so to find a critical angle, you may use of your refractive index 1.33. Okay, so sine C equals to 1 over 1.33. Then C is just your okay. Key into your calculator, you're able to find what's the critical angle. Then they ask you explain why light will not be able to image. Means total internal reflection. Okay, means over here.
Mr. Wong, the question say it will be able to.
Mr. Wong.
Oh yeah, so it will. Okay. Oh yeah, it says will. So but then but they gonna ask you to by calculating lah. So regardless, you still to calculate. Then you tell me that oh, the critical angle is larger than the so the angle of incidence is smaller than critical angle because 40 degrees is smaller than whatever I'm calculating here. Okay, that's why the light will be able to emerge from the water surface. So 1 mark for calculating critical angle, which you need to key to calculate to get answer. 2nd mark for explaining. Yeah. Why?
So,
Yes.
when I calculate the value, do I leave it to 3SF if it's like not it's more than like 2 dp?
For physics, it's always 3 SF.
Okay, can.
2 to 3 SF. So if something is let's say only like the answer
Wait,
is let's say
even for
2
angle as well, 3SF.
Angle usually you follow the 1 dp thing lah. But usually for physics, our angle rarely go below 10. So usually we'll have at least 2 dp. Yeah. Okay, so this one is you can calculate and draw the conclusion. Calculate the angle of refraction of the light ray which emerges from PQ. So, sorry, you are very choppy, I cannot hear you. So angle of refraction of the light ray which emerges from PQ. So it will be this one. It will be angle of refraction, meaning this one. Okay. So just key into your write down. It is denser to less dense. Okay. Then you just sub in. N is 1.33. I is 40. Here you can calculate. Speed of light in water. Wrong. My brain not working. Speed of light in water is V, not C. C is the speed of light in vacuum. So this is 3 times 10 to the power 8 meters per second, which I expected to know. That's when they never tell you. Oh, actually, they got tell you. I think because by this point, you haven't learned electromagnetic waves, so maybe they will just still give it to you. Okay, once you learn electromagnetic waves, you are expected to know already. Then they will not give you any.
So this kind of
Yes.
question, right? Is it like the usual kind of like average, normal like question for reflection and reflection?
I would say this is typical. You realize calculate here, calculate there is just your critical angle, your n equals to sine over sine r or sine over sine I, your n equals C over B. It's just these few things.
If let's say they would want to make the question harder, how would they do it?
Harder. I never really can think about it before. Harder, they can make it by context law, make it like a very hard to understand context. But calculation wise, it's just like that.
About the same lah.
Yeah.
Alright.
Okay.
Then is it you know all the like just now you're talking about those graph stuff where you talk about the different types of images like virtual, magnified, that those stuff that you're doing in class. Is there a way for us for them to like combine that and this as well?
Come again. Combine and what?
You know, like those questions where they ask you for the type of image, right? Will they ask you to deduce that kind of stuff by the calculations?
Via calculations. You're talking about lens, is it?
Correct, yeah.
So whether they can ask you like to give the characteristic based on whatever information you know.
Kind of, yes.
They can ask that.
Yeah.
Yeah, they can ask you application, they can ask you the characteristic of image, or they can ask you, oh, based on this characteristic of image, where should the what be positioned, that kind of stuff. Yeah. Okay.
Will drawing on the lens be commonly tested?
Commonly, you refer to what? O-level. O-level, I think I fit here as about
Not in O-level.
only appear 2 times, so 20% of the time.
Like EO.
I think the refraction one more often. If you can see the TYS, it appears more times. Okay, so over here, some of the things you actually know what is refraction, what is normal, what is angle of incidence, what is angle of refraction. And apply sine over sine R. You are able to define refractive index in terms of ratio of speed of light in vacuum to speed of light in medium. Explain what is critical angle, what is total internal reflection. Know the main ideas, apply in optical fibers and the advantages. Okay, then your lenses, what is focal length, define focal length, draw ray diagrams to illustrate the formation of real and virtual image by a thin converging lens. Okay, so basically everything that we have. Okay, so for lens, okay, so in this case, you will see that my image, so they say that this one is my image, so it's my object. So this one is very special. They give you object image, they never give you lens, they never give you focal length, right? Okay, so how do you, they are saying to draw a ray from here to indicate the position of the lens. Okay, so we know that just now I said before, any light that comes out from, let's say, the tip of the object, when it focuses, it goes back to there. Okay, so in this case, if I use a ruler, okay, I know a ruler, I'll just roll that. I don't anyhow draw, okay? You use a ruler, yours should be more accurate. Okay, so if you have this more accurate, they ask you where is the lens. Okay, so the lens, oh, okay, actually, I realize this is virtual. This is real. Okay, so my lens is where this one intersects here. Okay, because any light ray that pass through the optical center will not be refracted. Okay, so anything that pass through optical center will not be refracted. Then, so first you can label, you can find out where your lens is ready. Draw another ray from A prime to obtain the focal point. Label it F. Indicate the position of the eye. Okay, so the other ray will be the ray that when it goes parallel, okay, after it goes parallel, it will go through the focal point. But this light ray will extend from here, dotted line, then you draw. Okay, my drawing not soon again. Okay, so then wherever they intersect, this will be my focal point. Okay. Indicate position of the eye. Ta-da, that's all. Yeah. Okay, so sometimes lens question may not be so direct where they just give you object, give you focal point, give you lens, ask you find image. Then they give you object image, then you apply the key understandings. I think we still got a few more questions for lenses. Tomorrow we can finish up the workbook questions in class. Then yeah. Oh yeah, I didn't recap lenses. They only need me to recap.
Okay, Mr. Ong, before that, for this question, right, is based on what you memorize from like different type of drawings, right?
You can say memorized, you can say understood. Yeah. Because there's only one that you learn where the image is directly behind the object and is magnified and virtual. That is your magnifying glass. Where this is less than f.
Isn't that
So-
mirror as well?
Sorry?
Isn't that mirror as well?
Mirror, your image won't be behind the object. In mirror, you put your mirror here, your image will be opposite.
Oh, okay.
Okay, so maybe I just do a quick recap of the key stuff about lenses. Just the key things. Okay, so principal axis is this horizontal line. Optical center is the midpoint of the lens. Rays passing through optical center are not refracted. This is a very important rule. This surface along the focal point is what I call the focal plane. Just imagine I put a piece of screen over here. Okay, that'll be my focal plane. So the focal point is the exact point, okay, in which all the light rays parallel to the principal axis will converge after they pass through the lens. Okay, so this is the focal length, distance between optical center and focal point. Key learning, 3 rays of light. 1, anything at partial optical center will not bend. 2, anything that is parallel to principal axis after go through a lens will go through focal point. 3, anything that goes through the focal point after go through a lens becomes parallel. Yeah, just use this, any of the 2 to get apply and can get answer. Yeah. Okay, drawing. So then this one we go to the worksheet lah, okay? Because the worksheet that I printed for you guys. So same thing, if you need to recap, okay, these are a QR code you can scan for your worksheet. There's 6 different ones. I said that there is 4 of them that is more usually tested, which I expected to know how to draw. One is this one that we just drawn, right? So that the first ray, any light ray that pass optical center will not undergo refraction. Second one, any light ray parallel to the principal axis will go through the focal point. Then you realize that these 2 are moving further apart. Then I trace back my image will be here. Okay. Second one, not so common, so you can skip this. Third one onwards becomes very common again. Okay, your object distance between F and 2F, you draw, go through, you get this. So it's at 2F, you realize that the image and the object are same size. So it's like a photocopier. Then more than 2F, okay, it will become smaller. Infinity, like I said, usually we don't draw. Okay, but anything parallel each other they go through, they will converge along the focal plane, which is here. Okay. So this is the summary table of how it looks like. So there's object distance less than F, your magnifying glass. Object distance goes to F, your spotlight, usually not tested. Object distance between F and 2F. Object distance equals to 2F. Object distance more than 2F. Object distance infinity. Okay. So for each one of them, what is the image distance? Okay, this one I think no need to memorize. Okay. But important thing is the characteristic of image. You notice that anything that is less than F, you always be virtual upright. More than F will be real inverted. Why do we mention 2F? 2F is a special thing. Anything less than 2F will be magnified and enlarged. Anything more than 2F will be diminished. Anything that's 2F, then you'll be same size. So if you want to look at how it transition, okay, I think in class I showed this example. Okay, this is my focal point of 4. Okay, so my 2F will be 8. So you can see that if now I bring it less than 4, okay, I want it to be magnifying glass, so less than 4. Then between 4 and 8, this is so-called between F and 2F. So you can see that the image, right, is enlarged. You can see here my object image is only 1.19. Here my object height is 1.19. My image height is 1.94. So my image is enlarged, is bigger. But one thing to notice is as it moves further away, the image also gets smaller. The point at which they are the same is 2F. Okay, so you can see based on where you put your object, when you shift right, the image also change lah. Okay, so F will be same size, less than F will be enlarged, as in less than 2F is enlarged, more than 2F will become very small. Okay, that's the main thing about lenses law. Okay. Yeah, the rest are just examples. Any questions for me?
No questions. Yeah.
No, I hope I covered the whole of light, which was taught in many weeks in about 1 hour and 20 minutes. I go a bit faster because it's not the first time. Okay, I skip all the practical examples, which you all go back, you all need to go and try. Okay, do the past year paper. You can just go back to the lens question and try again. Okay, yeah. You want practice refraction just now? I uploaded some on Google Classroom, I think. Okay, so you can go and take a look. Well, it's MCQ lah. Okay, so the extra practice, I think. What happened? They're here. Okay, so this extra practice was, I think, I read this in 2017 when I was teaching 3A pure physics at the time. Okay, so I happened to dig it out and find it. And these are the other practice that you have requested before, like moments, vector diagram, all this, you can go back to this. Okay, so I'm just random practices that I find. Then yeah, Joshua, your request for the syllabus, I upload already. You go and see. Okay, the link is also there. Okay.
Oh, thank you.
You can see for other subjects also. Okay, any other questions for light?
Sure.
Yes.
Okay.
Okay, I stopped the recording first. I stopped the recording. Stop recording. So when you need to revisit this light topic,